Here's our list for Quiz 9 material. Let's talk about the sensation and perception first, then we'll come back and revisit the list to set up the states of consciousness material. This list here actually doesn't quite come from you. Didn't get a lot of feedback from students this semester, so actually I went back and picked the common difficult concepts from previous groups of students. And so with that in mind, I want to point out that there is one thing on this sensation and perception list that even though it's a common question, it's not something that we're going to need to talk about, and that's the parts of the eyes and ears. This is probably pretty good news for you, and that is you do not need to know the individual parts of the eyes and ears. I've got enough parts from the brain to overload your memory, so we'll take a little bit of a break for this for the exam. So we will go back and we'll take up absolute threshold and differential threshold, and then Weber's law, which is related to differential threshold. Top-down and bottom-up processing, we're actually going to wait. We won't do that in order because I have a special PowerPoint just for that. So we'll continue instead on to sensory adaptation, a pretty simple concept that will sound familiar to a concept from earlier in the semester. A couple of theories to help us understand color vision, trichromatic theory and opponent process theory, and then finally the principle of inverse effectiveness and superadditive effect of multisensory integration. The basic idea to start out with sensation and perception is in order to have sensation and perception, we actually have to get the outside world into the head somehow. Okay? Now, in other words, there are differences in physical energy out in the environment around us, and we have to get that to be represented as differences inside our brain, right? Differences that correspond to those differences in physical energy. And this can be at a very, very basic level. In other words, basic enough to say, is there something there or is there nothing there? So can we even detect the physical energy at all? And that's the matter of absolute threshold. Okay? It is the minimum amount of physical energy that you can detect. Probably the best way to have you understand this is to describe the way researchers used to discover it. Imagine yourself sitting in a completely dark room and you're staring at blackness in front of you. And the researcher is going to flash a very, very dim light. And they're going to ask you, did you just see a light? And you have to say, yes, I saw it, or no, I didn't. Okay. And keep in mind that half the time when they ask you, did you see a light, there is no light. So you can't just say yes every time. Okay. But suppose in this case there was a light and you didn't see it. It wasn't bright enough for you to see it. So then they shine flash a brighter light. Did you see it? Nope. A little bit brighter, a little bit brighter, a little bit brighter, and eventually you say, yep, I saw it. That's your absolute threshold. It is the minimum amount of physical energy, in this case, light energy, in order for you to be able to detect it. Now, if you're paying attention, that actually might sound familiar. Way back in the beginning of the semester, we talked about psychophysics. And I described it pretty much the same way, because, in fact, that is what psychophysics researchers were doing to a large degree. They were determining our absolute thresholds, not just for vision, but for all of the senses. So, for example, they could also sit you in a completely quiet room and then play a very, very, very faint sound. Did you hear it? Nope. Make it louder. Did you hear it? Make it louder, until eventually you say, yep, I can hear it. That would then be your absolute threshold, the minimum amount of physical energy, in this case, vibration of air molecules, for you to be able to say, yep, I heard it, I can detect it. Differential threshold basically works the same way, but in this case, instead of saying whether some stimulus is present or absent, we're just going to say, hey, there are two stimuli, and we want to find out what's the minimum difference between those two stimuli that are required for us to be able to detect the difference. That's why I like the second definition, or the second term, the just noticeable difference, because that reminds you exactly what this thing is. It is the difference between two stimuli that you can just barely notice. I should point out that when I learned differential threshold many years ago, the term that they taught me was difference threshold. So you will sometimes catch me saying that by mistake. It means the same thing, differential threshold and difference threshold, and also then the same thing as just noticeable difference. But the idea is just a simple extension of what I just told you about. So imagine, again, sitting in your dark room. Instead of just flashing one light, the researcher is going to flash two lights, and you have to judge whether those lights are the same brightness or different. If you see them, you say they're the same. Researcher will make them a little bit more different, until eventually you can say, yeah, I see the difference in brightness. And that then would be your just noticeable difference. Weber's law is an observation that differential threshold, that just noticeable difference, is not a constant amount. Okay? And I really do think that the weight example that they gave here is kind of the best way to illustrate this. Right, so imagine that you're holding out your hands and I put a 10-pound weight in one hand and an 11-pound weight in your other hand. And you can just barely tell that those two are different. So your just noticeable difference, if you're holding a 10-pound weight in one hand, is 1 pound. Okay? If I give you a 100-pound weight in one hand, pretend you're strong enough to hold that, and I give you a 101-pound weight in your other hand, you would not be able to tell the difference. Okay? So Weber's law says it's not the exact difference between two stimuli, it's that the just noticeable difference is a constant proportion of your standard stimulus. Right, so if your standard is 10 pounds in one hand, and you can tell the difference between 10 pounds and 11 pounds, that means your just noticeable difference is 1/10 of the amount. So if you had a 100-pound weight, you would actually need a 10-pound difference to be able to tell the difference. So 100 pounds in one hand, 110 pounds in the other hand. And again, that's Weber's law, and it applies to the differential threshold. Again, remember, we'll talk a little bit more about top-down and bottom-up processing later. I have a little bit of PowerPoint to share with you. So now we're just going to skip ahead a bit, talk briefly about sensory adaptation, then trichromatic theory and opponent process theory, and then back to the principle of inverse effectiveness and super additive effect of multisensory integration. So sensory adaptation. Basically, when we perceive something that doesn't change, we kind of get used to it. We don't notice it anymore. Okay? So, for example, you probably do not notice the elastic waistband on your underwear. Right? When you first put it on in the morning, you probably did notice it. You could feel it around your waist. But then as it stayed there the whole day, you ended up not noticing it anymore. You get used to it. That's sensory adaptation. that might sound familiar because it sounds a little bit like habituation that we saw way back in the factors influencing learning module, right? The idea that with the repeated exposure of a stimulus over time, we get used to it, and we notice it less and less. And this is sort of the same idea, although here with sensory adaptation, it's something that happens a little bit more rapidly, right? So habituation, typically we think of that as something that occurs over time. Here, it's on the order of a few minutes, right? If you put a watch on in the morning, as soon as you put that around your wrist, you feel it, and then a few minutes later, you don't even notice it anymore. So next we're going to talk about the trichromatic theory and component process theory, and this is in the context of helping us understand color vision. But you notice I stopped on the parts of the eye, but a few minutes ago I said you don't need to know the parts of the eye. You don't. There's not going to be any test questions about this, but I do want to point out that the way vision essentially works is you've got light that enters through the pupil, which is just basically a hole in the front of the eye. It gets reflected or focused when it passes through the lens, and it actually then shines an image of what you're looking at on the surface on the back of your eye. Right, so if you see the mouse pointer, and that surface back there is called the retina. That retina has receptors that are sensitive to light, and there are two basic types, rods and cones. Cones are the ones that are pretty much located here in the center of your field of vision. They are responsible, among other things, for your color vision. All right, so the trichromatic theory just notes that there are basically three different kinds of cones. Right? Cones that are more sensitive to red, cones that are more sensitive to green, and cones that are more sensitive to blue. Right? And so when you're looking at particular colors, right, color is really nothing more than a different wavelength of light. And so we have these cones that will fire more rapidly when you're looking at that particular wavelength of light. And through those three different combinations, red, green, and blue, you can basically mix them together in various proportions to allow us to perceive any different color. Okay. Notice the dates that we've got here: 1802, 1867. The trichromatic theory is obviously really, really old, and it is something that we still do use today as an explanation for the major portion of how we perceive color. But there is one additional phenomenon that pertains to color vision that the trichromatic theory couldn't explain. And that is this idea of after effects. So if you'd like to try an after effect, take a look at the green version of the Canadian flag on the screen. You look at it for 15 seconds, and then look off somewhere where there's you've got like maybe a white wall or a blank piece of paper, and you'll probably be able to see that Canadian flag in reverse. So go ahead and pause the video while you're doing this, and then go back and do that. See if you're able to experience that after effect. Right? If you do, you're kind of experiencing this effect of the opponent process theory. Okay, that again. Don't worry about details about the different kinds of cells, but we've got, as kind of the early part of processing of neural information for vision, we've got these cells called ganglion cells, okay? And they respond not just to a single color, but to pairs of colors, right? And they are the things that you kind of typically think of as opposite colors. So red and green, blue and yellow. And the idea is that if you're looking at a specific, say in this case green, for a period of time, it's kind of like you tire out that green response, okay? By looking, right, keep looking at green, you kind of fatigue that response, and then when you look away, the green can't fire anymore, and so what you got left over is the red, right? It's opposite. And so, again, that's just the opponent process theory. And honestly, it's not super important. And if really you just keep track of the idea that opponent process theory explains color after effects or color after images, then you should be okay. Okay, so then now last thing for sensation and perception from the textbook, before we go to the little PowerPoint, is principle of inverse effectiveness, super additive effective multisensory integration. We talk about the different senses as if they are separate, but of course our life is not like that. We have a single experience, and that experience uses really all of the modes of sense at the same time, right? So that's the idea of multimodal perception. When you are in a room with somebody, you're seeing them, you're hearing them, you're feeling things, with your skin, right, etc. Okay, the super additive effective multisensory integration just basically says or shows that if you get a little bit of stimulation from one sense and then a little bit of stimulation from the other sense, it can give you a tremendous boost in being able to perceive what's going on. Okay, so in other words, it's not just adding the amount of stimulation from one sense and adding the amount of stimulation from the other sense. You get actually more than that. Like, you can understand the whole thing. So, for example, you ever actually been watching something on TV and you're not really paying attention? You're turned away and you can't hear what's being said. Okay, but then if you pause the TV, rewind it for 15 seconds, and then you go back and listen again, but this time you're watching, and you can see the person on the screen and how they're moving their lips, you're actually able to hear it better. Okay, and that's the idea, that it's being able to see something and hear at the same time will allow you to perceive it better. Okay? The principle of inverse effectiveness sounds a little bit like the opposite, but realize what I just described, the super additive effect, it's when the stimulation is kind of small, right? You can't really hear it on its own. You can't really see it really well on its own. The two of them together will combine to allow you to perceive it much more effectively. On the other hand, with the principle of inverse effectiveness, suppose one sense is plenty for you to perceive it. Okay? You're sitting there, you're not even paying attention, but you hear a really loud and clear voice telling you to get into the kitchen. Okay? If you were looking at the person while they were saying that, it wouldn't help you that much, right? Because you already heard it well enough without that. So again, if the stimuli are kind of small or weak, okay, when you add them together, there's this really great boost from considering them together. That's the super additive effective multisensory integration. On the other hand, if one of the channels, vision or sound, is really strong, you're not going to get much added boost from any additional channels. If you can hear it really well on its own, seeing it's not that much help. So now let's spend a few minutes talking about top-down and bottom-up processing. Actually, this will be pretty short, but something that actually I really like a lot, and I even have a version of this this PowerPoint that takes over an hour, but I think I can help you understand kind of the key points in a relatively short period of time. And it actually starts with a kind of a poetic, well-known phrase. We see the world not as it is, but as we are. If you've heard this before, you actually may have heard it attributed to a number of different famous people. Nobody actually knows who the first person that said it was, so we have to keep it uncredited. And if you think about it, pause and reflect on it for a minute, it's really a very, very deep statement. But when we want to think about top-down and bottom-up processing, it's not technically correct. Really, the better way to think about it is sometimes we see the world as it is, or at least partially we see the world as it is, or sometimes partially we see the world as we are. And that then is the difference between top-down and bottom-up processing. Bottom-up processing. That's the part where we're seeing the world as it is. Okay? And if you see bottom-up processing described in other textbooks, you'll sometimes see it called data-driven because it's driven by the actual data, the actual features that are in the world itself. Right? So, for example, to give you a little bit of a summary of material stuff that you don't remember, with the parts of the eyes you don't need to know, but what happens is through sensory transduction, light enters through the pupil, gets focused by the lens, it shines on the back of the retina, which has these photoreceptors that will generate action potentials, and all the stuff you learned about from the neuron module. They travel out of the eye through a section called the optic nerve, where they go to the thalamus, which then recognizes it as visual information, and then actually sends it to the occipital lobes, where the primary visual cortex is. And that's primarily in that occipital lobes, that's where the bottom-up processing takes place. Right, so if, for example, you're looking at a vertical line, okay, you've got feature detectors in your occipital lobe that detect and say, look, he's looking at a vertical line. You've got horizontal line feature detectors. You've got curves of a certain orientation, lines at a 45-degree angle, lines at a 50-degree angle. You have all these very, very specific feature detectors that are basically lying in wait until you are looking at that very feature. Okay, and so think of it as building a recognition, building a perception by taking individual features and combining them and then building them up, sort of like building a house brick by brick. Okay, and that's bottom-up processing. Top-down processing, well, that's the part that's when we are seeing the world as we are, right? It's perception that our brain takes a very, very active role in, and is basically kind of guiding us to perceive things a certain way. And what I'll do is I'll describe two basic categories of top-down processing effects. One is Gestalt principles, and I put them in parentheses because it's not something that appears anywhere here, but we touched on Gestalt very, very briefly in the beginning of the semester, so it's worth mentioning again. And then we'll talk a little bit about expectation and context effects as another way that our brain will kind of guide us to see kind of what we expect to see. Like, So again, with the Gestalt principles, we first covered them way back in the history module, and what they did is they identified a number of perceptual principles for helping us kind of organize what we're looking at. So if we're looking at some scene, how we identify individual parts and how those parts are separate from others, and one of the main things that you might remember me talking about was this idea that the whole is greater than the sum of the parts, right? So we're going to see more than is actually there. Well, where does that more come from? It comes from our brain, right? So that's the top-down processing. It is our brain that is creating more than is actually there. So this is something I might have showed you earlier in the semester. If you're like most people, that looks like a giant triangle in the middle, but that's not a giant triangle in the middle. That is just 3 pink rectangles with wedges taken out, and then 3 angles. So something that suggests that there's a triangle there, but there is no triangle there. It is our brain that completes that picture. That's top-down processing. Our brain, all it needs is a suggestion that there's a triangle there, and it's going to finish that picture. If you're like me, you see the entire outline of that triangle, but it's not there. And the idea is that in the ordinary course of the day, we've got both top-down processing and bottom-up processing working together to allow us to perceive things efficiently, rapidly, okay? And it works something like this. You know, imagine that what we're trying to perceive is something really, really simple. It's just a letter on a computer screen, and the letter happens to be the letter T, okay? If you start at the bottom part of the figure, okay, the bottom-up processing is detecting individual features. There's a vertical line. There's a horizontal line. You put those together, and those combine to form the letter T. And at the same time, we've got our brain kind of guiding us as well, because something I didn't tell you yet is that T is not the only thing on the screen, right? It's the third thing on the screen, and the first thing was the letter C. The second thing was the letter A. Now we're looking at that third figure. We all read English, and we know that not every letter of the alphabet fits if that's going to be an English word, right? So that third letter is probably not going to be an A. Might be a B. It's not going to be a C. Might be a D, etc. And so the idea is, if we had no idea what letter it was, there'd be a 1 out of 26 chance that you know, you could get it right just by guessing, say. But now that we've ruled out some letters, right, instead of 1 out of 26, that's maybe 1 out of 10. And that's a much easier decision, figuring out what it is. That expectation that it's probably going to be one of this small sets of letters, or one of this small set of letters, makes it easier for you to recognize that. Okay? Now, the interesting thing about top-down processing is that it can be very, very powerful. And it can actually cause you to perceive things wrong, right? To perceive things as you are and not as the world is. So, this is 2 pictures of our dog, Ruggles. Ruggles died a few years ago, but he lived a long and happy life. And his long and happy life was primarily because my wife was really, really good about walking him. She didn't do it every day, though. And so she would actually look at Ruggles on a particular day, and she'd say, "Oh, look at poor Ruggles. He's so depressed because he didn't get to go for a walk today." Then she'd look at him on another day, and she'd say, "Oh, look at Ruggles. He's so tired because he went on a really long walk today." And I look at those 2 pictures, and I say, that's Ruggles looking exactly the same. So what is it that makes my wife say, on the left, he looks depressed, and on the right, he looks tired? Well, simply the fact that he's either gone on a walk or not gone on a walk. That sets up an expectation. He hasn't gone on a walk. I think he's depressed. He has gone on a walk. I think he's tired. So she's going to interpret that to be consistent with her expectation. Now, you might think, well, Ken, how do you know you're right? You know, maybe she actually can see things that you can't see. So I had to test this. Okay. So what I did is I snapped these pictures, and then about 3 weeks later I showed them to her, and she's like, "Yeah, that's right." I said, "Well, guess what? I tricked you, because the one on the right was actually the time that he hadn't gone on the walk. The one on the left was when he had gone on the walk. So indeed, it's nothing more than her expectation that makes her perceive these same poses as either being tired or being depressed." Tactile processing is actually pretty powerful, right? So you can probably read what that says, right? It says jump into conclusions, except it doesn't actually say jump into conclusions. And just by having an expectation, it can cause a pretty powerful perception. And it can actually lead us to get it wrong. Remember, it's seeing the world not as it is, but as we are. Right? And it might be curious. You say, why would we have this perceptual system that allows us to make mistakes? And that's where error management theory comes in. So you might remember from that module, we don't always perceive things right. Okay? We can make some mistakes, but not all mistakes are treated equally. There's some mistakes that are pretty dangerous and damaging, but that there are other mistakes that actually kind of make us safe. Right? So, for example, even though evolutionary psychology, we typically describe that as something that, kind of affected just 10 million years ago, you can think of it as a modern example of it as well. Imagine you're standing on one side of train tracks, and you need to get to the other side of the train tracks, and there's a train coming toward you. Okay? There are two types of mistakes you could make. You could say to yourself, wow, that train's coming really, really fast. I don't think I can make it across. Okay? But in reality, if you had tried, you would have made it across. So that's a mistake. The other mistake you could make is you look at the train, you say, that thing's a mile away. I'll make it easily. And then you try and cross, and you were wrong. Obviously, one of those mistakes is a lot worse than the other mistake. One of those mistakes gets you killed. The other mistake saves your life. That is error management theory. Right, error management theory says that, hey, when we're perceiving things, we're going to tend to make mistakes in ways that will keep us safe, that will keep us alive. So indeed, if you see something coming toward you, you'll judge its speed faster than if you see that same object moving away from you. Okay? That's sort of how top-down processing works. So think of it this way. Now let's go back to 1 million years ago, 10 million years ago. You live out in the wild, and you're walking around late at night, and you can't quite see, but you hear something off in the distance, and you kind of try to squint and see through the leaves of this bush, and you can't quite see what's there. Okay? Now imagine that you have two people right next to you. One of them is driven mostly by bottom-up processing, and the other one by top-down processing. Right? The one with the bottom-up processing stands there and waits until he finds out exactly what that thing is. He has to build all those features together and find out that it's a saber-toothed tiger that's about to pounce on him and rip his throat out. Okay? The other guy uses top-down processing. He uses this expectation. Gee, I think there are tigers around here. And as soon as you see something that hints that it's a tiger, you draw the conclusion. It's a tiger. Top-down processing led you to do that. The goal isn't to get it right. The goal is to make a decision fast enough for you to save your life. And it's okay if you get it wrong. So again, that's the idea of error management theory, right? So that we don't have to perceive things correctly. We want to perceive things in a way that's actually going to keep us safe. And sometimes that means making a mistake. You've seen this maybe on the swimming pool. All right? Go to a swimming pool that has a high dive and watch for a couple hours. You'll see this several times. Kids who standing at the bottom looking up, they think they can jump. They think they can do it. It doesn't look that high. But once they get up there, it looks a lot higher looking from the top and looking down. Right? That perception of that distance seems higher when you're up on top. That's the thing that keeps you safe. You're not going to want to go up there anymore. And again, that's what error management theory is. I think I've got good news. So as I return to our outline here and I look at the clock and see that it's 2:25 Friday afternoon, the lecture that I put together already is about 35 minutes long. I think that's enough. I want to get this out to you. For states of consciousness, let's actually not talk about those. Let's put that module into the pile of I didn't cover them. So again, that means it's on the exam, but you should be pretty comfortable just focusing on the quiz questions themselves. So you'll see basically repeats. And so just to summarize that whole list in case you lost track of it, the exam on Monday will cover quiz 7, 8, 9, 10, 11, and 12. But from quiz 9, states of consciousness will be mostly repeat questions from the quiz. From quiz 10, culture and emotions will be repeat questions from the quiz, and then all of quiz 11 and all of quiz 12. So I hope that eases your studying burden a little bit over the weekend, and I will see you on Monday.